questions from yesterday on the piecewise function section of your notes? We might have rounded slightly differently, but we should all be about the same. We talked about the answer to number 2, this first equation, in class because it was a constant function. So the other 2 would be the 2 that we are looking at. Okay, so sorry for my copying error. So correct the negative thing. Okay, so here's our calculator. Unfortunately, I can't reach it all, so I can't push all the buttons, but up there. But whenever we want to graph, most of what we're going to be doing has to do with these buttons up here. Okay? So I turned my calculator on. If there's anything there, you can clear it if you care. So the first thing we want to do is enter equations. So we're going to go right here to the y equals button. It literally gives you a list of y equals stuff. And then you can type in what you want. If you have equations anywhere in your list, just go ahead and scroll up or down to where something is written and press the clear button, and it will clear out any equations that are in there. All right, so now what we want to do is we want to learn how to type these equations into our calculator. So our first one that we call y1, we called them this on the worksheet so they would match up well with the calculator. We're going to enter in as y1 equals 1.4. So we literally just have to write y1 equals 1.4. The stuff to the left of the y1, y2, you can actually scroll all the way over there, and what you can do is change the way that those look. For the color calculators, you can change the colors and different things like that. Okay? So we're going to go ahead and type in 1.4 for y1 and scroll down. Notice that when I typed in the equation, the equal sign became bold. I can scroll back up to that equal sign and press enter on it, and I can turn the equal sign on and off, kind of, so to speak. Right now it's on, and that means whenever I graph anything, that line is going to show on the graph. So sometimes maybe you want to enter in a bunch of equations, but you don't want to see them all at the same time. You can turn some of them off and some of them on, kind of idea. Okay? All right, let's go ahead and enter in y2. Now, we have the variable x in y2. I understand that there are letters all over your calculator written in green. And if you ever want those, you can do the alpha and the green. But when you're typing in equations and you're trying to use the variable x, we use this key right here next to the green alpha button that has x, t, theta, and n. Those are all variables for different types of mathematical concepts. We're going to be using x, and our calculator is already in the right setting to do that. We won't really be using anything else in our course. So you want to put in 0.9x or 0.9x, and then plus 0.08. Down. And then we want to put our third equation in. Okay, don't forget the negative like I did when I was copying it. One small thing about your calculator. One button on here means minus, as in the operation of subtraction, and one button on here means make the number negative. Over here with adding, multiplying, dividing, that is the subtraction button. This is the negative button. Oftentimes, if you use the wrong one, you'll get an error of some kind. So think about that if errors come up on your calculator, like, oh, when I was typing -5, did I accidentally type -5, and the calculator doesn't know what I'm talking about, okay? So we want to make sure we use the negative button. So I'm going to type negative 0.7x plus 5.19. So I have my 3 equations in there. I want to go see them on the graph, but before I do this, right now if we all press graph, our calculators are probably in different places. Because if somebody's used the calculator before you, they may have graphed something else. And just like when you make a graph, you scale it differently depending on what you're graphing, right? Sometimes I need a lot on the x-axis here or the y-axis here. You can do all of that on the calculator as well. Okay? What we're going to do is we're going to go ahead and look at just the standard window on the calculator so that you guys always know how to get back to that. Okay? So if you want to change your own window, like I want to tell it how far to go on the x-axis from this minimum to this maximum and that kind of stuff, window lets you do that. We're going to go to zoom right now, the middle button up there. It has a bunch of different ways that we can zoom the graph where it will automatically zoom to different things. we're just going to go to zoom standard, and it's going to give us a 10 by 10, like 10 in the positive x, 10 in the negative x, 10 in the positive y, 10 in the negative y. Okay? So go ahead and choose 6. You can either scroll down and press enter, or you can literally just press 6. And it should then take you to your graph where you see this picture. Okay? Is this the picture that we saw, or didn't see, thanks to my technical difficulties, yesterday after the walking? No. Do we know our equations are good? What was the difference? So this actually is the next question on your handout. So after it said to graph everything, the question became, how could we create a graph that shows the changes in motion? Like our graph right now doesn't show the changes, right? It just shows everything happening at once. But when this was actually performed, it's like one thing was happening and then it changed, right? Then another thing was happening and then it changed and then another thing was happening. What would we have to do to get our graph to show that? What essentially do we need to be able to do on the graph? What would you want to do? Do we like the way the calculator drew it right now? No. What would we like to be able to do in order to show what we really saw on the CBR yesterday? Yeah, like combine the lines. Can like one go and then stop, right? And then can you connect it to the next one and then have it stop, and then can you connect it to the next one, right? So basically, we need to be able to impose some limitations, okay? We're not going to do that on the calculator today, but we are going to learn how to write that so when we read it, we know what people are talking about, all right? So we're actually going to take a pause from the calculator activity for a minute and come back to it. And the next page in your note guide, so you're going to leave that page kind of halfway and go to the next page, and it should look like this. So we're going to take a break and come back, because the next thing it said was write the equation, but we have this big question of like, well, how do you write it and tell it to do this one and then stop doing that one, and then do this one but then stop doing that one, right? So we're going to figure that out. The first thing I want you guys to go ahead and do, and I'll do it up here while you're doing it at your desk, is I want us to graph these 3 linear equations. These are all things we should be capable of graphing, right? 2x plus 1. Okay, this one has some fractions. Don't freak out, right? 7 over 2 is like 3.5, and so you have to go down 1 over 2. No big deal. Okay, you can handle it. And then this one is a constant. So go ahead, graph them, check with your neighbor, make sure they're right while you guys are graphing them. Okay, so you've had some discussion about it. I hear people talking, deciding. Some people are highlighting. Okay, so here is the line that is the graph of this. So this is what I've drawn for my first graph, okay? If I'm going to highlight the portion of this graph that's in the domain of x is less than 1, which part of the line should I be highlighting? Yes. Good. Okay, so everything over here is good, right? And then all the way up here, when do I have to stop? When x equals 1. So here's when x equals 1, which coordinates to this point right here on my graph, right? So I'm going to go all the way up to that point. Is that point included in highlight? Actually, 1 does equal 1, so I would put that open point right there to highlight. Sorry, my highlighter's thick. I have to make it really big, okay? So I would highlight everything, and I want to mark the end point so I know where it ends. I just don't want it filled in because I don't want people to think that point is included, okay? So then if I want to highlight on the next graph the portion of that graph that is within the domain when 1 is less than or equal to x, which is less than 4, what portion of this line am I highlighting? What point should I put my pen on to start? 1, but like right here 1? 1 on the line. If I didn't know where that was, could I quickly plug 1 in here and figure out where it was on this line? Yes. Okay. So 1 comma whatever this is, which happens to be right here. Is it included? Yes. Okay. So this is actually a point. And then am I shading upward or to the left along this line, or downward and to the right along this line? To the right, because I want from when x is 1 until it's equal to 4. So that's kind of the area I'm looking at, but I want the portion of my line that falls in that area. So I would highlight all of this. And then when I get to the point that lines up when x is equal to 4, is it included or not? It just says x is less than 4, so I don't want to include that point, but I still want to mark it as a boundary. Okay? Then on the last graph, I would like to shade the portion of the graph that falls within the domain where x is greater than or equal to 4. So that means from 4 over, right? So on the x-axis, that means from here over, but I need to mark it on what I have graphed. This end point right here that's with 4, is it included? Yes, because of the equal to. And then the whole thing to the left. Okay? So that's basically what we wanted to be able to do on our graphing calculator, right? We have these 3 separate things that span the whole graph when you just graph their equation. But what we want to say is we want to say, please use only this part and then stop here. And then use this portion of this one and then stop there. And then use this portion of this one, and it can either keep going or stop depending on what the scenario is. And now we want those 3 portions to all be on the same graph together. Okay? So look at the notation right below this on your note guide. This is how they would tell us to graph something like that. They would say, graph 2x plus 1. You guys already did that, right? But then to make a point where it stops, notice that next to it they write only when x is less than 1. So am I allowed to graph the whole line I originally graphed? No, only the part I highlighted, right? Okay. Then they say graph this second line. We already did that. But they tell you you can only graph it from 1 to 4. So not the whole thing, only the part that you highlighted, right? Then graph this third constant function, and you're only allowed to graph that when x is greater than or equal to 4. Notice how this is written kind of weird? So f of x is like y. That shouldn't be something that's too strange to us. Notice it doesn't equal one thing. It equals a whole bracket's worth of things, right? Okay, and when we did our little experiment up here last time, let's say the ticker went on for a really long time, and the person did like 10 different motions. How many different pieces would our graph have? 10 different pieces. How many different equations would show up in our function? 10, with all their limitations written next to them. So do you understand how this notation works? And this notation is what allows somebody to know not to just like scatter all the things on the graph, but instead split them into these pieces that start somewhere and end somewhere, and then the next one starts and ends, and the next one starts and ends. Does that make sense to everybody? Okay, so we just want to understand how to read the notation. So you're going to build right here the graph of this piecewise function. So how are we basically going to do that? Good. It's combining all the top graphs, not the whole things, but which parts of them? The highlighted parts, because we highlighted the parts that we wanted, right? So it's basically putting those 3 sections together onto this graph. So go ahead and do that, and I will do the same. Oops. If I do it right. You have yours right in front of you, so it's better. So here's my first piece from my first graph, right? Then I go to put on the second piece. Now, this is a kind of a nice piecewise function because the second piece, so this one ended at 1 and didn't include that point. This one started at 1 and did include that point. This one ended at 1, 3. Where does this one start when we plug in 1? Look at your graph and pick out the first point you highlighted, or literally plug 1 into this function. -1/2 times 1 is -1/2, plus 7/2 would be 6/2. 6/2 is really 3. So this graph has the point 1, 3. Happens to be right on top of the point I didn't highlight, but now I have an included point sitting right on top of the not included point. It's not going to look any different than any other point on the graph then. It's going to look like it's just been included because they overlap. Does that make sense to everybody? Okay. All right, and then go ahead and graph your second function. Okay. And so you have that portion of it, and then it stops at the point 4, 1.5, and that's open. But the next portion of the graph also includes the point 4, comma 1.5, and has it closed. So again, that open point is going to get overlapped by a point that is included. So it's just going to look like it was included as part of the graph. And then we graph from 4 over using that constant function. So it's just the 3 pieces you highlighted. Is this a function? How do you guys test if something is a function? So it's in the summer packet. It's from Algebra 1. Good. So when you have the graph, the vertical line test is handy. We're technically looking, does any input have more than one output? So when I pick this x value and I look at my graph, is there more than one point on the graph lined up with this x value? No. So that's what the vertical line test is quickly doing for you. Okay. This totally passes the vertical line test, right? Or every input only has one output. So that means, yes, this is a function. Second question, is it continuous? So continuous means exactly what it sounds like. Can you draw this entire graph without ever picking up your pencil? Yes. How would the graph have been made discontinuous? What could I have done with my equations or my limitations or whatever to make sure it was not continuous? Okay, I could have some parallel lines in there. Okay, what else? Right. Okay, so, or what if it did include 1, but I changed like a value over here, right? Then this one would still have a point at 1, but would it necessarily land nicely right on top of the other endpoint? No. So might you see functions where one ends and the other one starts somewhere else and then goes? Yeah. Okay. But this one's continuous because we can draw it without picking up our pencils. Domain. Okay. So domain is left and right. Are there any limitations on x? Is there any x that you could pick out on the x-axis and say, aha, Ms. Dahl, I found one. If you use that x, you cannot find a point on the graph that matches up with it. Are there any x's that meet that criteria? No, which means all the x's work for the domain. So what's the domain going to be? All real numbers. Another way to look at it, right here, it's basically spelling out for you your domain, right? This function only exists when x is less than 1. But that captures all the numbers up until 1. This one then captures all the x values from 1 until 4. And this one captures from 4 on forever. So was there any numbers I missed or skipped? No. Okay? So the domain is all real numbers. The range is easier to find if you look at the graph graphically. Okay? Did you have a question? Sorry. No? Okay. All right, so let's look at the range. So now we're focusing up and down, or y values. Okay? So is there any y value you can find that the graph does not capture or reach? Yes? Right. It doesn't reach anything up here. Does it reach everything below that? Yes. Are there any gaps? No. So basically, I want to say that my range, the numbers that I get as y values, are everything from here and below. So I would say that y is less than or equal to 3. Are we okay with that? So that's how you graph a piecewise function. Okay. Obviously, there are like shortcuts. Like, do I have to draw all 3 graphs and highlight every time and then put them on the thing? No. But if I'm stuck, could I draw all the graphs separately, highlight them, and put them on the thing? Yeah. Okay. So we could definitely do that. So going back then to our scenario with the CBR. Oops, actually, I put these in the right order. Smart. What if we were going to write an equation for our scenario that came up here? We saw when we put them all in the graph, it puts them on there, but not in the right order and not with the right limitations. So let's think about how we would write our equation. So first of all, does one equation describe the motion that we saw yesterday that was gathered by the CBR? No. Okay, so when we need more than one branch to our equation, you'll usually see this bracket there indicating that we have multiple things going on. Yes, Jordan? Oh, okay, yeah. So what should my first branch say? Uh-huh. Good. So what this is saying, and depending on how you guys interpret the situation, I would be okay here with greater than 0 or greater than or equal to 0. Like you could say he started there at 0 seconds, so at 0 there would be the point there. It's a real life scenario, so we'd have to decide exactly how we want to interpret it. So he stood there from 0 to 1.2 seconds. Does anybody know why she's saying x was equal to 1.2? Yes. Good. We said his constant, his standing still, ended on the little tick marks at here, and then it started the new branch. So do you guys see now why we made a note of that? Because we know that to write the function now, we need to tell someone, only do that up until this point, then stop graphing that one and start graphing a new one. Okay? So somebody else, give me the next one. What is the next branch going to be? Yes? Okay. And what are the limitations that we place on it? Okay, good. It's less than 3.3, but it can't just be forever less than 3.3, or it's also going to graph over here in this one section. So what other limitation has to be placed on it? Yes. Good. And then you guys have to decide here again, like which one of our graph was continuous, right? So clearly 1.2 was included. So given the real life scenario, there would be a little leeway here. You have to kind of like, are you saying it's part of this branch, or are you saying it's part of this branch? Okay. It overlaps, so it wouldn't really matter, but pick which one it's going to belong to. All right, somebody else new, give me the third branch of our piecewise function. Yes, Michelle. Good, and what are the limitations? Good. And again, that was the end of the graph, so we could include 5 because I think it did go all the way up and include the 0.5, comma, whatever on our graph. Okay. Notice ours doesn't continue forever in both directions. We had a stopping point. What would our domain be for this graph? It wouldn't be all real numbers. We didn't spread over the whole graph all the x's possible. Okay. What's the smallest possible x that you can use according to what we have up here? 0, right? And then you can go from 0 to 1.2 using this, and from 1.2 to 3.3 using this, and from 3.3 up to 5. And then does anything else exist? No. So what would be our domain? 0 to 5. And that would be it. Everything from 0 to 5, because we saw the graph and it was continuous. Okay? But only from 0 to 5. Okay? And then our range would depend on our highest point and our lowest point reach, and it would be y values sandwiched between, kind of like the x's were sandwiched between 0 and 5, between whatever the highest height that our walker reached and the lowest. Does that make sense to everybody? Yes. Okay. So little challenge for you guys. So tonight's homework is a worksheet on graphing piecewise functions. So you're going to get equations like this. You're going to be expected to graph them. If you're struggling, graph them separately. Decide which parts you want to put together on your graph, right? Okay. So it's a worksheet. It's already posted, and you'll be able to work on that. What I want you guys to try and do right now, kind of a challenge at the end of class, is see if you can answer these 3 questions right here based on a scenario. So number 10 is a scenario similar to what we created, but it helps really see if you can put together the concept of what the distance time graph would look like, how many different pieces are really happening there with the way he's walking, and then could you put together an equation. So work with your groups and just see how far that you can get on this. And we'll discuss the answer to this tomorrow, and then we'll let you check your piecewise function homework, okay?